Okay, so off we go, and picking up from where we left off last time, we were talking about parameterizing surfaces. It's, again, not a single algorithmic method for how to do it. There's various different tools that you can use. Tools for the toolbox, per my favorite metaphor. And here's the next one. Sometimes the best way to create to make a parameterization is to create your own brand new tailored coordinate system. Okay, so I'm just going to show you an example of how this works. I think this is the best way to do this. So here's what's called a torus. And suppose I want to parameterize this surface. How would I go about parameterizing this surface? Okay, so so here's the idea. Let's just ask, how would you, if let's suppose you lived on a planet that was this shape, right? Y'all okay? Okay. So if you lived on a planet that was this shape, right? What would be the longitude and latitude equivalent, right? I mean, how would you describe? I mean, you wouldn't go around talking about rectangular coordinates, right? You wouldn't describe this point by its x, y, and z. That'd be silly. We don't do that on planet Earth, right? We have two coordinates to describe where we are in our two-dimensional surface, right? And it's very efficient. It's tailored to the shape of the Earth, etc. So here's one way that you can do it. There's many different ways you could do it, right? I think this is a reasonable choice. You pick a starting point like that, right? And actually, let me zoom so I can see a little bit better. In fact, let me switch to pencil mode so we can get more fine with it. You pick a starting point, right? And whatever point you want to get to, what I would do, I think would make the most sense, is let's talk about by what angle do you need to kind of rotate sort of upward, you might want to call that northward perhaps, right? From that starting point. And then from there, by what angle would you want to rotate kind of around the hole, if you will? And maybe I'll call that S. And I think that makes a lot of sense. I think this will get us anywhere we need to get on the surface of the torus, right? And these two numbers, notice it's tailored to our surface. We have exactly two coordinates for describing location on our two-dimensional surface, and it'll be hard to beat that. Right? Now, there's something arbitrary about the starting point. Yeah, sure, fine, no problem. Right? You could start on this point in the back, or maybe some point over here on the side, whatever. But I think this would be something structurally kind of like this is a good way to go. Does that seem like a good starting point? Good. All right. So what to do with this? How does this give me a parameterization? Oh, I have to do like this. Here we go. How do we get a parameterization out of this? The big idea is to use these coordinates and just solve for rectangular coordinates. We're basically just going to create a coordinate conversion system, right? Coordinate conversion formulas. So now there's a lot of little micro details in here, and the micro details I'm going to leave for y'all to look through. It's a combination of vector geometry and just regular old geometry and some trig and a little bit of linear algebra, a combination of different things that y'all know how to do. The broad brushstroke strategy, though, is, and let me zoom in a little bit more again, to notice that vector is easy to write down. This vector is not too hard to write down. Of course, it is going to depend on that angle. It's going to depend on that angle t, which you see in the formula. Make sure to check this. Make sure you can see where this comes from. Right? A little bit of trig, a little bit of geometry. And make sure you can do that. And altogether then, that'll give you, I'm going to call this point P. That's not exactly what I want, but that is kind of the first step in the process. And then the next thing I would do is notice that I can take my P, I need to zoom out a little bit more. There we go. Take that point P, and notice all I have to do is rotate by our angle S, counterclockwise around the z-axis. Just do that rotation. By the way, a little bit of linear algebra. Here's how you do that rotation, counterclockwise around the z-axis. Make sure you can do that. So again, linear algebra, linear transformations are always matrices. Matrices are understood by columns. Columns are the images of the standard basis vectors, all of that business. Make sure you can produce this matrix as needed. And, well, take that rotation, apply it to the point P that we just wrote down a formula for, and the result is the coordinates of your point X in rectangular coordinates that you were trying to find in the first place. Okay, so summarizing what we had here, if I can get this to cooperate, there we go. The big idea is we create a coordinate system. Given that coordinate system, we find a formula that gives position. Oh gosh, I don't know what happened there. That was weird. Okay, I don't know why that did that. Oh gosh. Can I get that to disappear? There we go. Solve for rectangular coordinates in terms of that coordinate system and celebrate. We're done. We actually have now a parameterization. Notice this gives me position, x, y, and z, right? Rectangular coordinates of your position, and notice they are functions of two parameters, s and t, those two parameters being our coordinate system that we made up, that we tailored for our particular surface. Does that make sense to everybody? Just kind of just an example of how to use this idea. This particular coordinate system makes sense for this particular surface. If you had a different kind of a surface, you'd want to tailor a different coordinate system. Every example is going to be different. You kind of have to think about the geometry. Okay, but again, tools for the toolbox. Okay, last one, and then we will move along. Sometimes you already know how to parameterize something really close to what you're interested in. Not quite. Right? Basically the big idea is if you have some existing parameterization and you just want to tweak it a little bit, roughly speaking, go ahead. Right? Just make sure you understand how the tweak works and how you can tweak toward something specifically that you need. So for example, let's start with the unit sphere. Rectangular coordinates, rectangular equation like that. I'm going to say we already know how to parameterize the unit sphere. We have a method for doing that. I'm going to refer you back to Friday's lecture, and we talked about graph parameterizations. And this you can do with the spherical graph parameterization because, in fact, this sphere is a spherical graph. I've solved for one of these spherical variables, rho, as a function of the other two spherical variables. In fact, they're really convenient, super easy. One of my favorite functions of the other two spherical variables, just one, right? I don't see the phi and the theta, no problem, still a function of phi and theta. Okay, so you plug that into the conversion formulas and out comes this parameterization of the unit sphere. Which you can rewrite if you choose with a bunch of equations. That's just sort of expanding out the individual coordinates. Not much happened there. Okay, so, what if I want to parameterize this ellipsoid? Now, that's not a sphere. But you will notice it's not that different from a sphere. Right? They're pretty similar. Look at the equations even. They're very closely related equations. Right? So the idea is that, well, if I know how to parameterize this, and if this isn't that different, maybe I can take this parameterization that I have, figure out how to tweak it, and then that'll be a parameterization of what I want. Okay. So the foot in the door is to notice that all we have to do is basically stretch it out. And so how do we do the stretching? Well, let's see here. I can tell how the stretching worked. I can see the stretching happening. right there. For example, this is stretched in the x direction by a factor of a, right? Flashbacks to chapter 2, right? In chapter 2, we talked about how if you everywhere in your equation, if you replace x with x over a, that stretches by a factor of a in the x direction. Okay? Likewise y, likewise z. So here's the thing, if that's the stretch, right, how does that affect the parameterization? Well, exactly the same way. Because after all, this parameterization of the sphere is a bunch of equations. And I can do the same move. Just in that equation, all of those equations, just replace x with x over a. That's the same stretch. Just doing it to the parameterization now. And that gives me now a new parameterization like this, which of course, you can collect back into a vector form of the parameterization like that. Everybody see what happened there? So, tweaks. Now here's a different take, right? I came at this first from the point of view of how to basically view this in terms of equations, because we already knew how to do that, right? We've seen examples previously of how to tweak equations, turn them into new equations that do what we want geometrically. Right? So, okay, but let's interpret now. What does that look like when you're looking at, the vector form of the parameterizations? And I think there's a pretty nice take here, and that is, look, this formula, wrong color. This formula for x, there it is. All I've done to stretch by a factor of a is to literally multiply it by a. Right? So that's another perfectly reasonable take. Now, it is easy to get confused. Wait a second, when do I multiply? When do I divide? You want to make sure to distinguish between what you do to an expression giving you a value of x versus what do you do to how the variable x shows up in the equation. Right? So I think it's pretty easy to see that these two different forms down here are really saying the same thing. It's just a matter of cross-multiplying the ABC. Not terribly different, really. Anyway, just make sure to keep that straight and don't divide when you should multiply, etc. Okay. What do you think? Everybody happy? Yeah? Question?
Well, this is not a question, but just in terms of usage, did it ever show up that we have a p-value that's like a squared times b squared times c squared, and we have to go back from whatever format back to this?
I guess I don't quite understand.
Just more so like, if you were to write this out fully, it would be x squared over a squared, y squared over b squared, etc.
Yep.
And then if you were to move the values to the other side, could that technically be a new p-value? I mean, we'd have...
You say p-value. I don't know what you mean by a p-value.
Like the...
Oh, you mean row.
row.
I understand.
Yeah.
No, I hear what you're saying. There is a temptation to look at that and say, well, that's the same as that, right? But what you have to keep in mind is that the only reason that works is because this is literally row squared, right? And this right here, it's just not, right? It's not row squared. It's not easily relatable to row. So yeah, I mean, I hear where you're coming from, but I think it's not going to work out very nicely in that sense. Yeah, that's a good thought. Yeah. Right. Okay. All right. So let's move along. Quick comment. There's a bunch of other examples in the book. In fact, I think now that I think about it, the book actually does the torus example. But all the book examples have a certain common feature, and that is they're all what I'm going to call kind of backwards. At least they're certainly backwards from the examples I've showed you. In the examples I've showed you, we find ourselves looking at some sort of a surface, Maybe we're given the equation of the surface. Maybe the surface is described geometrically, whatever. We're given some surface, and the question is, how do I create a parameterization? The book's examples all start with a parameterization. They give you a parameterization, and then just ask you, how do I infer what the surface is that it parameterizes? Right? Now, that's a useful skill as well. The reason I show you examples that go, I want to say my way, is twofold. First of all, the book already has a bunch of examples going their way. Right? The other reason is, in my experience, the way I'm doing it is what you're going to encounter in the real world and applications of where you need to do something with a parameterization. Most of the time, in my experience, the parameterization does not come pre-given to you. That's just not how it tends to work. It tends to work as sphere. We need to do something on a sphere, and then you've got to create the parameterization. Right. So that's why I focused on how to create parameterizations. The book's examples are about interpreting parameterizations. So, anyway. All right. So this next page here, and my pencil's doing something weird. This next page is doesn't quite make the cut for spending class time. Now, I'm not going to cross it out. This is not stuff you don't need to know. It's also pretty non-critical, right? So if you don't read through this, you can get away with it. It's okay. But I do think it'd be a good read. I do think it's a pretty readable little discussion. And, of course, this is just sort of supplementing what's in the book. So I encourage you to look at this stuff. It is useful ideas. But we don't have the time to go through all this, and again, tough choices and all that, and it's not such a big loss. I'm going to take us down to the next page here and kind of pick up from this point. You'll notice that we have here a parameterization, right? We have points on a surface, our surface in this, just to have an example to draw, I have points on a sphere here. And those are given as functions of points in a parameter space. And I'm using the spherical graph parameterization. So x, y, and z are functions of phi and theta. Right? Oh, I'm sorry, yeah.
Is the above page still fair game for exams?
I mean, I don't want to say no, but I also don't want to say yes. I wouldn't think that I would. I wouldn't think that I would craft a question that was about that page specifically. But let me say, I think there are ideas there that will help put this stuff into a little bit of. If you're interested in why what I'm about to tell you is true, then that page that I'm skipping is good for that. So yeah, I wouldn't expect it to be the focus of an exam question, but it might be useful in helping you understand stuff that is fair game. Does that make sense?
Yes.
Yeah. Yeah. Okay, so this is a parameterization. We've got x, y, and z as functions of phi and theta. And here's the thing. If you were to start moving in the phi direction, I can tell you exactly what happens when you do that on your surface, right? If you're moving in the phi direction, phi increasing while theta is staying constant, you're going to be going kind of south, right, on the sphere. And likewise, I can talk about moving in the theta direction. And what happens if we move in the theta direction? Well, theta is going to be increasing, and we will be moving east on the surface of the sphere, right? Okay. And then I can ask reasonable question. Let's see, let me get rid of that and this. I could ask, okay, if I have some little piece of area in the parameter space, d phi d theta represents the area of that little rectangular region there. And if I want to ask what is the resulting area Oh, color choices. I'll use yellow. Oh, that doesn't show up very well, does it? Let me make a different color. Ooh, Okay, red. Fine. If I want to know what is the image area, what's the area of this little, basically, approximately parallelogram here on the surface? What's the factor, right? By what factor do I multiply that area to get that area? And we've done this kind of thing in several different previous contexts. You could probably guess what's about to happen. We're eventually going to be doing a pullback, right? We're going to be interested in stuff happening on the surface, but we want to understand it in terms of what's happening in the parameter space where it's flat and it's easy to do business. Right? So we need to understand the stretching factor. What do you multiply by that orange to get this red? And you can kind of see this coming. You can see that we've got a little parallelogram. How do we find the area of a parallelogram in space? Flashbacks to Chapter 1 and Math219. It's the magnitude of a cross product. And with that noted, let's see here. So red, this area in the surface relates to this area in the parameter space by way of a stretching factor, and that stretching factor is this formula right here. It's the magnitude of the cross product of the two partial derivatives of your parameterization. And again, if you want to see all the details of where this comes from, I mean, this is a lot of it right here. But where did these come from? These came from the previous page, and if you want to read that previous page to see that, that's totally fine. A reminder, also, perfectly good stuff for office hours. If you want to come ask me in office hours, I'm happy to go through the whole thing with you. No problem. Okay. So there's our stretching factor. And it turns out, let's see here. I'm just going to try to get this ideally zoomed. This vector, let me just clean up here. This vector whose magnitude is our stretching factor, and let me emphasize again in purple, this is our stretching factor. That's how much things get stretched. The vector whose magnitude does that is an object of interest, and we're going to give this a name and a notation. This cross product we're going to call capital N. Capital N because it's a normal vector. It's a normal vector because, and I'll go back to where we were in just a second, it's a cross product of two tangent vectors. These partial derivative vectors are tangent vectors. Again, if you want to see why, you can look at that page that we just glossed over. And when you take two tangent vectors and look at their cross product, you're going to get a vector perpendicular to the surface, aka a normal vector. Okay. All right, so it is a normal vector. The name that we give to it, it is the parametrized normal vector. And I'll come back and talk about that in a moment. And so that gives us a rephrasing of our stretching factor. Our stretching factor is just the magnitude of capital N. That's basically, I just compactified this formula into a single name so that the formula would be a little bit easier to write down. Is that cool? All right, so we talked about why it's a normal vector. It's a normal vector because it's perpendicular to the surface. Why do I call it a parametrized normal vector? There's a really good reason for this, and you can see it right here in the formula. This thing depends on the parameterization. Right? You can see how the parameterization is where the capital N comes from. It is computed from your parameterization. And I want to remind y'all, this is an important fact to always kind of keep in mind. Parameterizations are arbitrary. Surfaces have lots of parameterizations. When you parameterize something, you're making something up. You're pulling it out of a hat. You're creating it out of whole cloth, right? Pick your favorite. colloquial expression. So it depends on the parameterization, and that's why I think it makes sense to emphasize that. I mean, have that disclaimer right there in the name. This isn't the only normal vector. This is the one that comes from your parameterization. So I call it the parameterized normal vector. Okay. I think that's a reasonable terminology. Now, that said, the book chooses a different name. The book calls this the standard normal vector. I think that's confusing. Let me tell you why I think that's confusing. Standard makes it sound like there's something about it that's intrinsic to the surface. And again, very importantly, it's not intrinsic to the surface. We got this from the parameterization. The parameterization's made up. There's a lot of them. Different parameterizations will give you different parameterized normal vectors. I just feel like the word standard suggests a little too much. I feel like it suggests that there is, again, something universal about it, something like it's the only one, or something. And I think that's misleading. Okay, quibble about the language. All right. So let's do something with all of this. We're going to compute the area of the unit sphere. I will acknowledge that y'all already know the formula for the area of the unit sphere, right? Flashbacks to high school geometry. You probably previously computed the formula for the area of the unit sphere. That's a single variable calculus problem, right? There's clever little arguments you can make about, you take your sphere and you kind of slice it into a bunch of little onion rings, and you look at each onion ring, and various arguments you can make about how much area there is on each one of those things. So this is not an example that can only be solved by this method. The purpose of this is just to get our feet wet, get some grease under our fingernails. Let's actually use this stretching factor that we've done to actually compute something. And the fact that we already know the right answer is going to be satisfaction at the end that, okay, we know now that this method works. Okay. So the big picture strategy is going to be that we're going to be adding up a bunch of little pieces of area. And if I want to compute the area of the whole thing, I just need to add up a bunch of these little pieces of area. Each one of those little pieces of area is going to be my stretching factor multiplied by these little pieces of area, d phi d theta. And all I have to do, if I want to get the whole sphere, I'm just going to have to look at all of the values of phi and theta. I mean, the ones that give me the sphere, right? So theta is going to go from 0 to 2 pi. Phi is going to go from 0 to pi, the usual for spherical coordinates. And all I got to do is each one of these d phi d thetas, I just have to multiply by whatever that stretching factor ends up being to get this area that I'm actually trying to add up, and then just do the resulting integral. So as you will have noticed, we are going to need to know what that stretching factor is in order to be able to do that calculation. So that's the first step here. We got to parameterize and compute the stretching factor, and there's a bunch of trig in this, and tough choices and all that. So I'm not going to walk you through all this trig. I'm going to walk you through the structure of the calculation, and y'all are going to check the trig. And I think this is again, healthy exercise. It's one thing to know kind of what's going on, but again, you do have to rubber meets the road. You do have to actually be able to execute the calculation. So please do go through this. Please check the details. Please make sure you can do each one of these steps, and make sure you have all of the prerequisite trig skills and remember the various identities and all that stuff. So here we go. Here's our parameterization. This is the rho equals 1 spherical graph parameterization. We take the appropriate partial derivatives with respect to our two parameters, phi and theta. Make sure you can do that. We do the cross product. Oh, wrong color. I used orange for that. Do the cross product. There's a lot of yada 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 on that. Make sure you remember how to do cross products. Make sure you are good enough with the trig to be able to put that all together. And this is what you'll end up with when you do that cross product. And remember, the stretching factor is the magnitude of that cross product. And this is, I'm going to say, an unexpected result. Good unexpected. Look at this monster that we were dealing with. This, the cross product, the actual capital N vector is not pretty. But wonderfully, when you compute its magnitude, it simplifies super nice. It's just sine phi. Again, fair amount of effort to go through and carry through those details. Pythagorean identity figures very prominently in making this simplify in magnitude to just that. So make sure you can do that. Make sure you can fill in all those blanks. Oh, yeah. Mm-hmm.
Is that the partial with respect to phi and then theta?
Mm-hmm.
Oh, okay.
Yep. Two separate partials.
Two separate ones.
Yeah, that's right. Yep.
Okay.
Yes. Yeah, sure.
Can you explain just very briefly
Mm-hmm.
when you drew your green arrows, like how you got there?
Oh yeah, just taking the partial derivative. So, so just as a, real quick, taking the partials with respect to phi. Oh, let's do this in green to be consistent. Partials with respect to phi. Alrighty. Well, the partial with respect to phi of this. Well, keep in mind that means theta is constant. That means cosine theta is constant. The cosine theta comes along for the ride. And the partial with respect to phi of sine phi is cosine phi, etc. Yeah. Okay. Sine phi. So that's our stretching factor. And remember, that's all we really needed. We were going to add up a bunch of little pieces of area on the sphere. Area on the sphere is stretching factor times area on the in the parameter space, and we have our stretching factor. Stretching factor we just computed was sine phi. So our D capital S just turns into that. We're adding up over the entire sphere, where these are the values of our parameters to get the entire sphere. And check it out, we have an easy double integral. Make sure you can do that. Okay? And there's your final answer, and it's what we knew already that it was. It's 4 pi. Yeah?
I'm just a bit confused. So we took the cross product to get the area, and then we're going to integrate it over the entire boundary?
We got the cross product to get the stretching factor.
Yes,
yeah.
And then you took the magnitude to get the area.
The magnitude to get the stretching factor for the area. So the little piece of area on the sphere is ds, and that's stretching factor times area in the parameter space, dp d theta. Yeah. Yep. Okay, so that's just a first example. Get our feet wet. Many more to follow. And a quick reminder of the players involved. Oh, I'm sorry, yeah.
So the purpose of that calculation was just to find the surface area?
So, yep, surface area of the sphere. That's right. Yeah. Okay. So, here's our various players involved. We have a parameterization. Position on our surface is a function of parameters. In general, let's call them S and T. You can call it whatever you want. I was using phi and theta because we were thinking about the sphere specifically. And let's see here, a little piece of area in the parameter space, resulting little piece of area in the, I can't use that color, red, okay, a resulting little piece of area on the surface itself, stretching factor to figure out what, how much that gets stretched out, and that stretching factor, we agreed, is the magnitude of capital N, which is computed by this formula. Capital N does have both a direction and a magnitude. Let's see here. We'll use red here. The direction is indicated by a unit vector. The magnitude is, just the magnitude. And so sometimes, by the way, this unit vector is useful. Now let's take a moment to recognize where this unit vector came from. This is the unit vector that comes out of the parametrized normal vector. So hopefully no surprise, I'm going to call this the parametrized unit normal vector. Right? And that is going to come up. That is going to be useful. We are going to be doing stuff with that in a little bit, not just at the moment. Again, we already know the formula for this magnitude. It's that cross product. By the way, you can write that out in coordinates. Nothing happened here. I'm just expanding all the coordinates of those partials. And by the way, you can actually crank out that cross product. And this is a healthy little exercise. It's not even a big one. It's a little bitty healthy exercise. Crank out this cross product. Write it all down. And what you will find, I think surprisingly, is that these individual coordinates, you'll notice I've written them using a notation that we used long ago back in chapter 5 when we were doing change of variables. And this notation we used when we were talking about two-dimensional change of variables stretching factors. That's not what this is. This is a surface that we're playing with stretching factors of. How come there's two-dimensional stretching factors showing up when this is kind of a three-dimensional problem, right? So this is what I like to call an eyebrow raiser. That's weird. This is suspiciously suggestive that there might be something going on here. There might be a good reason. This might not be a coincidence, right? And I'll go ahead and give it away. It's not a coincidence. There's a really good reason why two-dimensional stretching factors come up. And again, if I had the time, if I had 15 minutes to kill, which we don't, right? But if we had 15 minutes to kill, I would love to show you why this is. It's ultimately very natural. If you're curious, come on into office hours. Very happy to discuss. But for Math219, you don't technically need to know, and so, oh well. Okay. All right, here's a special case. This is a very useful special case. I encourage everybody to make sure to know this special case, but I emphasize this is a special case. This only works in the special case. This is not a general alternative. You have to know the general formula, right, from parameterization. But however, in the special case that you're looking at a graph, and furthermore that you are using the graph parameterization, which of course we recall the graph parameterization looks like that. Right? That's our graph parameterization. In that case, well, you could just straight up compute those partials. That's what they are, every time. And you can compute this cross product. That's what it is, every time. And you can compute the magnitude. And that's what it is every time, right? So this is a fantastic little formula to make sure that you have memorized. When you're using the graph parameterization, boom, there's your stretching factor. You don't have to write down the parameterization, take the partial derivatives, do the cross product, write down the magnitude, right? You can just go straight to this. And it's a nice little time saver. It's a nice little, mistake avoider, right? So definitely ought to know the formula, but I emphasize this is not an alternative. This is not a general alternative because it only works if you're using the graph parameterization. So please do keep that in mind. Okay.
Quick question.
Yeah.
Isn't that implying that x equals s and y equals t?
Yep, absolutely. That's how the graph parameterization works. The graph parameterization is where you take your input variables and let those equal your parameters, and then let Z has to be what it has to be, and the parameterization follows. So that's from Friday's lecture. Yeah. Or was it Friday or was it Wednesday? It was from last week. Yeah. Yes.
So we only use this if it is a graph parameterization.
Only if it is a graph, and only if you are willing to use the graph parameterization specifically. Yeah. Because there's lots of ways to parameterize. Just because something is a graph doesn't mean you have to parameterize it that way. So this is a narrow special case, but it's a special case that comes up actually pretty often. So handy to have this in your toolbox. Okay. All right. Now, I'll make a related observation. Look at this part of the formula and think back to chapter 2. That is, in fact, just the square of the magnitude of the gradient. Okay, think back to chapter 2. What's the formula for the gradient? How do you compute the magnitude? This little part is, in fact, magnitude squared. And then furthermore, let's look at magnitude of the gradient. That tells you how steep your graph is. Again, flashback to chapter 2, old news. So another way to think about this, pretty useful in some occasions, is that if you're using a graph parameterization, and if you want to know what your stretching factor is, it says right here, your stretching factor only depends, by way of this specific formula, sure, but it only depends on how steep your graph is. That's it. If you know how steep your graph is, you're in business. You don't even have to parameterize. If you know how steep your graph is, do this little number, you've got a stretching factor and you are in business. So I'm going to show you a really cool example. This is very real world. I have done this in my own house in a, I think, important application. And let me describe the scenario first, though. Suppose I want to compute the area of my roof. By the way, this is not exactly what my house looks like, but it's easier to draw. And so I'm going to, do like this. So we have various different faces of a roof, and y'all have seen a million roofs, and y'all know what I'm talking about. So like this, and then you continue to go all the way around, etc. Okay. Someday, if you buy a house, you're going to have to probably pay somebody to put a roof on it at some point. Because roofs have a finite lifetime, and you're going to have to replace them periodically. And they're really expensive. Like 5 digits expensive. Like, oh my God. Right? And so, super duper expensive. And some company is going to come, right? And some guy with a name tag here is going to tell you how much it's going to cost based on his calculations. And you may or may not want to trust him to have done that calculation. Right? So, if you want to double check and make sure you're not getting overcharged to the tune of possibly several $1,000s, right? Here's a little slick move that you can do. I think this is a lovely calculation. Realize that your roof is not only a surface, but it is a graph. Right? Passes the vertical line test. So I could say, I can parameterize this with the graph parameterization. And another really cool little fact, and by the way, every house is different, and this does not apply universally, but surprisingly often, in most cases, how steep the roof is approximately constant. And this is the case for my house, for example. Well, if that's the case, if your steepness is constant, and let me put this in gray, representative of the fact that steepness is constant. If steepness is constant, and if your stretching factor only depends on steepness, that means that your stretching factor is constant, and therefore factors right out of your integral. And the nice punchline then is that the area of the roof Oh, gosh. The area of that roof, which, by the way, what's your alternative to how to compute that area? You're going to get up there, you're going to climb up to the top of a 2-story house and, just hang around on a sloped, 35 feet off the ground, concrete down here to fall onto. I'm not doing it. Pass. Nope, not going to happen. And then, by the way, even once you get up there, what are you going to go up there with a protractor and measure that angle? Right? And you're going to measure every single one of these distances, and then you're going to get out a piece of paper and do a ton of geometry because none of these angles are right angles. That's really inconvenient geometry and arithmetic and measurement, and everything about that is super inconvenient. When all you have to do to compute that surface area is just measure the area of the footprint. That's easy. Rectangles. Every one of these angles is a right angle. Certainly they are at my house. Maybe a few exceptions, creative architecture here and there, maybe not, right? But in most houses, it's a rectangular, pieces of rectangles anyway, footprint, super easy calculation, multiplied by the stretching factor, which is easy to measure because it's a constant, and boom, the surface area of your roof. It's a much easier way to do it. I've done it in my house. I confirmed that they did not rip me off, right? And by the way, for whatever it's worth, I've double-checked a lot of things related to, life, while adulting, right? And I have caught mistakes. I'd have to sit down and really think about it, but it's been at least 4 or 5 or 6 times. Weirdly, all the mistakes I caught were in their favor. What are the odds, right? What a coincidence. And I've saved myself something like $6,000 by catching mistakes by checking up on their arithmetic. And whoopsie, you catch the mistake, and there you go. Right? Yeah, you have a question. Yeah.
Is this the same technology? Is this the same math they would use in their technology?
I don't know how they do it.
Oh, okay.
Yeah, I'm pretty sure that name tag is not using multivariate calculus. I don't know what they do. I have no idea. Yeah, they might actually climb up there, and I don't know. Right? Yeah. Right. Okay. So anyway, cool method. Let's see. We have a couple of minutes left here. I'm going to plant a thought, and then we'll call it a day. So the idea here. What is a surface integral? Let's see here. Oh, you know what I'm going to do? I'm going to do that. Ooh. And then I'm going to do this. And no, wrong button. Sorry, I hit the wrong. There we go. And let me do this. Okay, so going back to chapter 6. Y'all remember, beginning of chapter 6, the very first thing we did is we said, I want to do an accumulation argument, chop it up, add it up, whole the sum of the parts, but adding up over a curve. And, look, we just had to confess that this is technically not a kind of integral we've ever written down before. So, okay, fine, we write down a new Riemann sum, but it's just the whole is the sum of the parts, and on each little piece you take stuff per unit size and multiply by size. Right? It's just the same fundamental idea behind every other integral we've ever done. We just did it here for curves in space, as opposed to three-dimensional solids, two-dimensional planes, and one-dimensional intervals. Okay. Suppose we want to do something on a surface. Right? How are we going to chop it up, add it up on a surface? Same basic idea. I'm going to chop it into little pieces. I'm going to argue on each piece that on that little piece there, I'm going to look at, that's hard to read, isn't it? I'm going to look at stuff per unit area times area. Right? So if this is the side of this is a mountainside, hillside, whatever, and I want to there's some kind of little flower that's growing on the side of the mountain, and the higher you go in altitude, the fewer of those flowers there are because of weather or whatever. Okay, you want to find the total number of flowers growing on that hillside. Okay, well, you're going to look at each little piece of hillside, and on that piece of hillside, you're going to talk about flowers per unit area times area, and then you're just going to add up over all of those pieces. Right, now, computationally, how do you actually do that? Okay, technical details we'll get to. But strategically, the whole is the sum of the parts, and on each part, stuff per unit size times size. It's like every other integral we've ever written down. So this is called a scalar surface integral. We use this notation, and it's just like line integrals with a different geometry, and we will pick up here next time and talk about how to compute them. See y'all later. Have a good one. Don't forget about attendance.